Okay, Year 12, this is just a video where I'm going to give you some feedback about what I noticed in our exam that we took. Okay, so we had 10 multiple choice questions. Notice how I had the time down there for 20 minutes. I feel like many people might have taken too much time on this one, but let's see how we go. Okay, the first question, we're finding out which has the highest molar solubility. That is going to be the largest KSP value. Okay, the largest KSP value because it's products over the reactants, so the more products means it's more soluble, and that was calcium carbonate. Okay, here what we had is we had a reaction, and I was asking you for the correct equilibrium expression, and remember it's products over the reactants. And what do we leave? The other thing that I was testing you out is the states. Okay, aqueous can change concentration. Aqueous can change concentration. Aqueous can. Liquid cannot change concentration, so it will not go in the expression. So hopefully you didn't find like C or B. You can cross out because they had water in there. And so A and D, if you look at them, they're just mirror images of each other, and so you should notice that the products over reactants is the D one there, so that one was D as well. Alright, should I highlight it? D. Okay, here we had a good old classic Le Chatelier's problem, isn't it? We're doing something with equilibrium. Okay, so it's exothermic, because we have a negative enthalpy, so heat goes on the right. Which of the following set of conditions would produce the highest yield? So we want more of the phosgene, which is this product here. So we want to push the equation to the right. So we need to take heat away or cool it. Need to cool it, and also look at the number of moles, because we've got a homogeneous gas reaction. 2 moles on the left versus 1 mole on the right, so pressure. High pressure will also favour. So we're looking for cool or low temperature, high pressure. Low temperature, high pressure was B. Alright. 4, we had a nice simple definition one. I think most people got this right. I think everyone did. Bronsted-Lowry talked about acids are, remember I told you to change that, acids are proton donors. I don't think anyone had a problem there, which is great. Okay, moving on to the next page. pH, given we've got a hydrochloric acid solution. Notice it was a monoprotic, so it's just a negative pH. Sorry, a negative pH. pH equals negative log to base 10 of, because it's a monoprotic and strong acid, you can just put the concentration in, it'll all go over to the right. Okay, and that ended up being question 5 was D, so the 1.74. I don't think many people had a problem there. That was good. Question 6 was a variation on a good old past HSC that I really like, this one. So if 1 gram of each of the following compounds is treated with excess hydrochloric acid, which is going to give the greatest volume of CO2 at a certain temperature and pressure? Okay, so here you need to make the connection to 1 gram of each. If I want the most volume of CO2, I want the most moles of CO2, and the most moles of CO2 are going to come from the most moles of reactant, or which one of these carbonates. And the one that has more moles in 1 gram is the one with the lowest molar mass. Okay, so they're all the carbonates, so let's disregard the carbonates, and all they're differing is by, are they lithium or sodium, and do they have a hydrogen in there? So lithium has a lower mass than sodium, so we can cross out the sodiums. And 2 lithiums versus a lithium and a hydrogen, well, the lithium and the hydrogen has the lowest molar mass. Okay, the isomers of the C3H6FCl, most people started to get there, but there ended up being 5 of them. I think at least half people got the 5. I think a few mistakes were people got 4. They didn't get all the variations. So practice those type of questions, because they come up a lot, of trying every combination. Okay. Question 8 Of all the following all the following compounds have similar molar masses, which has the highest boiling point. Okay, so we're looking for intermolecular forces. The butane just has dispersion forces between two molecules of butane because we've got no polarity in there. Propan-1-ol, the OH bond and the CO bond there is polar. So you got polar regions there of the alcohol, and it also fits the hydrogen bonding criteria. So that's fairly high. Two molecules of propanol stick together quite well. Ethanoic acid, we've got more polar bonds and stronger polar bonds, so stronger hydrogen bonding there. Ethanoic acid has the highest boiling point. Down to propanone, we have got a polar bond there, the carbonyl, the C double bonded to the O, but it doesn't fit the criteria of hydrogen bonding. So two molecules of propanone will only stick together with at most dipole-dipole attraction. So it's ethanoic acid because hydrogen bonding and really, really strong hydrogen bonding too. Okay, number 9, the following balanced equation, fermentation of glucose. Well, why do we ferment glucose? We want ethanol. We want alcohol. Okay, so look at this. A, that's not ethanol. B, there's some ethanol. C, we don't want carbon dioxide and water. Go away. And D, we've got some ethanol there. So it's between B and D. Okay, the other products are, actually, the biggest thing I'm looking at is D, is oxygen there. Now, remember, we don't want oxygen in our mix. We want it anoxic because the ethanol will oxidize to ethanoic acid. So oxygen cannot be one of the reactants. So hopefully that leads you to B here. Okay, so we've just got as a reactant there, and we could have a catalyst being yeast. We just have C6H12O6, or I'm trying to think, is it sucrose or glucose? I think it's glucose. Okay, it's the sugar anyway. And we're getting ethanol and carbon dioxide bubbles out. Okay, so it's B for that one. 10 was an old past HSC question that I really liked, testing you on AAS, and the answer for that was D for this one. The wavelength of light used, so those cathode lamps, specifically matches the spectral lines produced of the sample. So if you're analyzing lead, you want a little lead lamp in there. Okay, these questions here. Question 11, we've got our equilibrium there, and we had our initial. Look at this, initial, final. So you had to do an ICE table here. Okay, so equilibrium expression, nice easy marks there. Most people did pretty good. Calculate the K value, you needed to do an ICE table for that. So if you had some trouble, practice doing ICE tables. And most people did quite good with the consequences of increasing the temperature. Okay, so they recognize that was endo, so heat is on the left. So increasing the temperature would, among other things, drive the forward reaction. So the easiest you could talk about is that the concentration of iodine would increase, or the concentration of chlorine would increase, or the concentration of the ICl3, whatever that's called, would decrease. A few people went in to talk about the value of K, which was really good too. Question 12, most people did okay, about 2 or 3. Only a few people got 5, because you had to kind of go in a bit of detail there, and it really helped out too if you connected it to the current Lewis theory as well. Okay, so a few people started to talk about, because the question is about acids, a few people started to talk a bit too much about bases. Now, you could occasionally mention the definition of a base because of the contrast of it, but if you're talking about the limitations of a model and you're talking about bases, not a good idea in a question about acids exclusively. Question 13, look at this, another simple pH question of a monoprotic strong acid. A few people had trouble with question B, and these are quite common problems, and it's just a limiting reagent problem. You need to find out what's the limiting reagent. You need to find out what's in excess. And whatever's in excess, find the concentration of, and if it's higher so if the H plus but ends up being in excess, put it in the pH equation. If the hydroxide ends up being in excess, put it in a POH, then convert it over to a pH. Include a balanced chemical equation. Most people did really good with that too. Question 14, we've got the sodium hydroxide titration with ethanoic acid. Okay, just a classic titration problem. The endpoint, calculate. So very, very direct titration, straightforward there. Not a hard one at all. I think most people did good. If you're struggling with that still, please get onto that because you should have that ironed out for your final exam. B. This is a very, very common problem, explaining why the pH of a resultant salt is non-neutral. Okay, so most people struggle with this one. So remember, the thing that you need to do is show that one of the ions reacts with water. To produce, if it produces H3O plus, it's an acidic salt, or if it produces OH minus, it's a basic salt. And here we had the ethanoate ion. So here, the ethanoic acid is you also needed to mention ethanoic acid is a weak acid. So its conjugate base, the ethanoate ion, which I've just drawn there, is relatively strong, and it's strong enough to react with water. And I'm showing this through an equation. It's an equilibrium though, and it reforms ethanoic acid, and it's taken that H plus away from water, so it's left OH minus. So I've reacted part of the salt with water, and it's made some hydroxide. So we have a basic salt there. So please put in a formula. Please practice those. Those questions are not too hard. Talk about your conjugates. Show a reaction with water forming either H3O plus or OH minus. Okay, here we talked about our alkene and how we test for it. A few people really, not so much, they did struggle with it. They started to mention we did tests with ethene. Now, while that has a double bond in it, sure, and you can add across it, we certainly didn't use that in the lab because it's highly flammable. So that was a bit of a laugh there, okay? What we did use was cyclohexene, okay? And we used it in the fume cupboard. One double bond cyclic. So outline a procedure. Most people did pretty good with that. And most people did pretty good with saying it was the loss of the brown color if they use bromine, or the loss of the purple color if they use permanganate. Please talk about we use permanganate because it could come up in a safety question. A few people struggled with the equation though, so practice onto that. It just comes down to those addition reactions that we learned. Question 16 was a conversion factor. So part A, you didn't need to know anything specific, but you needed to be able to convert these two and work out a numerical problem. And most people did pretty good there. Part B was the advantages and disadvantages of bioethanol. Yeah, and most people did well there too. That was not too hard. Okay, they come up all the time. All right, question 17. A few people had trouble with A because we're talking about a substitution reaction with something with a double bond, and people started to get confused and started to do an addition reaction. Keyword, substitution reaction. So I was talking about how you can change ethene into chloroethene, or ethanol chloride, okay? The precursor to PVC. And then part B was showing how you get one monomer of the vinyl chloride and make it into polyvinyl chloride. Most people did okay on that. Okay, question 18. A few people had troubles with this one, which is a bit disappointing. So go back and look at the process of gravimetric analysis. Not so much the first problem, but evaluating the validity, okay? I gave you such a small method here that there are a lot of assumptions in it. So you can poke a lot of holes into it, okay? So look at this. The student weighed out 1.2 grams of fertilizer. Okay, nothing more. So one thing that is left out there is when you sample something, you want to sample a homogeneous representation. Okay, so you'd say something like the fertilizer bag was homogenized, and then 1.2 grams was taken, kind of thing. If you just let gravity settle it out and you sample the top of a fertilizer bag compared to the bottom, you're not going to get an even what's the word that I'm looking at? I'm looking for an even, you're not going to get the same sample. I'm saying consistency. Well, that's true, but it's not going to have the same words. You know what I mean, though. You're probably yelling out the word that I'm looking for. It's going to be different. Okay. After that, it was dissolved in water. That's good. That's what we do next. Okay. And then they're talking about adding the barium chloride. Usually after we add the water, we filter out any insoluble stuff in there, okay? If you don't filter it out, it's going to make that insoluble stuff is then going to be mixed in with your barium sulfate that's formed and add to that mass, okay? So what we're assuming then is we made the assumption that there's going to be no insoluble stuff in the fertilizer, and that's not true, okay? So 50 ml of the barium chloride was then added. Okay, it just gives you an amount. What we do then is we roughly add some amount in until we see no more precipitate forming, and then we add a little bit more just to make it safe. We really want to make sure that the barium chloride is in excess, okay? We want excess barium chloride there to make sure that all the sulfate is mopped up. If we just put a certain amount in there, how are we sure that the barium chloride is in excess, okay? After that, a white precipitate as barium was formed, which weighed, okay? How did they weigh that? Okay, if you filter off your solid barium sulfate afterwards, the first thing that you should do is dry it. It's going to have a lot of water in, okay? So we assume that it was that all of that barium sulfate that was formed was dry, but it actually had water in it. So it's terrible, a terrible method there. So a few people did okay on that, but most people didn't do good. And validity, remember, what are we assuming? What have we assumed? What are we assumed? What are we assuming? All right, and that will get you through most validity questions there. Know your method and know what we've assumed. What have we skipped out? Okay? All right, hopefully that helps you out. Thank you, Year 12.